A massive dark void is devouring everything in its path, including a likeness of Earth, and it's astonishing to witness the first image of a black hole in space. Black holes are infinite monsters that consume everything, including light itself. Formed from the remnants of dying massive stars, these black holes possess an incredibly strong gravitational pull that distorts space and time, ensnaring everything within their gravitational grasp, including time itself. A recent discovery from the James Webb Space Telescope challenges our fundamental understanding of the cosmos. How does this finding challenge our long-held beliefs about the formation of galaxies? Does this significant deviation pose a threat to Earth? Join us as we explore how the James Webb Telescope has identified an enormous dormant black hole near our solar system. Black holes are indeed fascinating entities. Searching for the first one was quite a challenge. While Einstein's theory of relativity predicted their existence, black holes do not emit any light like stars do. Their size and spectral properties are the only measurable characteristics we have. Now we have visual evidence confirming their existence, yet definitive proof of black holes was lacking for a long time. The first known black hole, SG Mark, was discovered in 1964. Stephen Pedling and Kip Thorne, two of the foremost experts on black holes, didn't reach a consensus on whether SG Mark was indeed a black hole until more than 30 years later. Thorne believed strongly in the existence of black holes and focused on them throughout his career. However, the question of whether scientists could find one remained unresolved for many years. Pedling was somewhat anxious about the lack of discoveries, so he supported his bets with his research. He mentioned that he and Thorne were about 95% certain SG Mark was a black hole by 1975 when the wager was first made. By 1988, they still could not reach a definitive conclusion, but by that time, Pedling was forced to concede the bet in 1990 when sufficient observational evidence was amassed to confirm it contained a black hole. Thorne claims that Pedling waited for the perfect moment to admit defeat. 2 spacecraft were launched into space on a suborbital rocket, leading to the initial discovery of SG. A star signal was detected by the spacecraft, which allowed astronomers to pinpoint its location 7,200 light-years away, highlighting a massive blue star orbiting another large object. This second object was also emitting strong X-rays, consistent with being a black hole. Much research has centered on SG since it was identified as the first black hole in the universe in 1964. Yet it still holds more surprises for researchers. New studies indicate that this black hole has a mass 70 times greater than that of the Sun, earning it the title of the largest known stellar mass black hole ever discovered without the aid of gravitational waves. This finding raises doubts about long-held cosmological assumptions regarding the formation of black holes. The stellar winds blowing from a star's surface cause it to lose mass to its environment, but to have a black hole of such magnitude, we must consider a reduction in mass loss experienced by bright stars over their lifetimes. SG Mark breaks records in multiple ways. Its incredible mass is just one of them. SG Mark also has the fastest rotational speed of any known black hole, approaching the speed of light. A black hole with such a high rotation does not conform to the typical model of black hole evolution. Although definitive proof of black holes has only recently emerged, it is becoming increasingly clear that they are scattered throughout the universe. Thus, even if astronomers ultimately unravel all the mysteries of SG Mark, its numerous counterparts still hold many surprises. Within 2,000 light-years of Earth, researchers have identified a dormant giant, the Milky Way's largest stellar black hole, with a mass approximately 33 times greater than that of our Sun. Despite being the second closest known black hole to Earth, the dormant Gaia BH3 remained unnoticed until it was accidentally discovered in a flurry of data and observations compiled by the European Space Agency. Gaia BH3 is located in the constellation Aquila. The team noticed something unusual while analyzing data from the mission, which aims to create a three-dimensional map of our galaxy. A star wobbling 1,926 light-years away had a peculiar trajectory that indicated it was trapped in orbit around a nearby massive black hole. To confirm the mass of Gaia BH3, astronomers and ground operators employed a large telescope from the European Southern Observatory in Chile to validate their findings. They determined that once every 11.6 years, the wobbling star completes an orbit around the black hole. The discovery of this previously undetected high-mass black hole surprised everyone. Gaia BH3 is a type of black hole formed by the collapse of a star, known as a stellar black hole, and it is the largest of this kind found in our galaxy. As a dormant black hole, it is not actively siphoning energy and material from a companion star, which makes it less detectable in sky surveys. Stellar black holes in our Milky Way typically have a mass of about 10 to 20 solar masses, with SG Mark holding the record at about 70 solar masses. Gaia BH3, with a mass of 33 solar masses, remains relatively small compared to all black holes. For example, the central supermassive black hole in our galaxy, Sagittarius A*, is 4 million times larger than the Sun. Gaia BH3 is the second closest black hole to Earth, following Gaia BH1, which is 1,500 light-years away and has a mass 15 times that of the Sun. Astronomers now have more evidence to determine how stellar black holes formed from the collapse of massive stars, making this discovery all the more significant. Stars with lower concentrations of heavy metals are believed by cosmologists to be the source of larger stellar black holes. Hypothetically, these metal-poor stars, composed primarily of hydrogen and helium, are thought to experience slower mass loss, leaving more material available to form more massive black holes when they die. However, researchers lacked a reference point until they discovered Gaia BH3 and its companion star. In the early universe, there were massive black holes, some millions or even billions of times more massive than the Sun. Recent observations suggest that these enormous dark openings played a significant role in the development of both black holes and galaxies, highlighting a complex relationship that remains largely unclear, akin to the classic chicken or egg dilemma. Scientists are still trying to determine which came first, the galaxies or the black holes. The size and formation of these primordial black holes are still shrouded in mystery. Researchers have found potential evidence that microquasars, black holes that consume stars, might be the driving force behind the production of high-energy cosmic rays that reach Earth. These supermassive black holes consume material from nearby giant stars within binary systems, and as this material is directed toward the black holes, some of it is expelled as relativistic jets traveling at incredible speeds. A microquasar is essentially a less powerful version of a quasar, both powered by supermassive black holes that accrete nearby matter. First identified in 1912, cosmic rays can hit Earth with astounding energy levels, reaching up to 20 electron volts eV. Far more energetic than particles produced at the Large Hadron Collider, the largest and most powerful particle accelerator on Earth. The prevailing theory suggests that the most powerful cosmic ray accelerators in the universe are supernovae and microquasars. However, until recently, there was limited evidence linking microquasars to the acceleration of particles to such extreme energies. Using the High-Energy Stereoscopic System (HESS) to detect high-energy gamma rays from jets emitted by the most prominent microquasar in the Milky Way, the research team established a connection between cosmic rays and microquasars. Known as SS433, this microquasar's jets interact with surrounding matter, creating shock waves that accelerate electrons to energies sufficient to explain the particles detected in high-energy cosmic rays. Although the acceleration mechanism in SS433 is similar to that found in supernova remnants, the more powerful shocks in supernova remnants can propel particles to even higher energies due to their greater speeds. The intense radiation emitted by SS433 suggests that these cosmic phenomena should not be overlooked when trying to understand the origins of high-energy cosmic rays. SS433 was the first microquasar ever discovered, identified in 1975 and included in a 1977 catalog of celestial bodies. It gained fame when science fiction author Arthur C. Clarke listed it among his 7 wonders of the universe. The system consists of a white giant star and a black hole, which has a mass around 10 to 15 times that of the Sun, located at the center of the supernova remnant known as W50, approximately 18,000 light-years from Earth, affectionately referred to as the Manatee Cloud. S433 has been the subject of extensive study for decades. The two components of the system orbit each other approximately every 13 Earth days, separated by around 15 million miles, a distance roughly one-third that between Mercury and the Sun. The immense gravitational pull of the black hole strips away the outer layers of its companion star, causing a portion of this stripped material to be consumed by the black hole, while the rest forms an accretion disk around it, influenced by strong magnetic fields. Some of this material is ejected at speeds around 26% of the speed of light, forming jets that spiral in a corkscrew-like pattern, creating lobes that shape the W50 supernova remnant. This remnant was formed when a massive star exploded about 20,000 years ago. The two lobes created by the microquasar within W50 give it a resemblance to a giant manatee, which is why it has that whimsical name. Radio waves can detect the jets of SS433 up to 1 light-year away from the source. Interestingly, these relativistic jets can dim and become undetectable due to energy loss, yet they re-emerge as high-energy X-ray photons nearly 75 light-years from the microquasar's origin. This suggests that the particles expelled from a black hole are being propelled to even higher energies by something within each jet. The HESS collaboration utilized 5 telescopes to study these unique gamma-ray jets emitted by SS433, with findings indicating that the double system is situated further from the source of the more intense gamma rays. The team concluded that gamma rays, which are particles of high-energy light, can be best explained by rapid shocks accelerating electrons in 2 regions approximately 75 light-years from the central plane of SS433, where shocks are bending jets into tight beams and enhancing the energy of the accompanying particles. The research team aims to unravel the remaining mysteries surrounding this intriguing microquasar. Part of their investigation involves identifying the sources of the jet shocks, which have been detected at distances from the binary system where they originated. Additionally, the team will seek to expand their findings on microquasar jets to those produced by larger quasars powered by supermassive black holes. While these results clearly indicate a possible origin for high-energy cosmic rays, they do not yet solve the cosmic mysteries that have persisted for a century, including the nature of black holes and dark energy. The James Webb Space Telescope, JWST, is expected to focus on these topics in the coming years, exploring primordial quasars and the characteristics of the first black holes. Over billions of years, researchers hope to understand how these black holes may have influenced galaxy formation and how these astronomical giants achieved their vast masses when the universe was less than 1 billion years old. With JWST, astronomers can investigate whether a massive molecular cloud that formed about 13.2 billion years ago might have collapsed directly into a heavy black hole seed, as well as seek answers to how the universe expanded so rapidly. Studying objects from the early universe is a primary mission for JWST, which, while designed to observe distant celestial objects, will also be used to investigate elements within our solar system during its third observing cycle. Researchers utilizing the James Webb Space Telescope, JWST, have discovered a remarkably red supermassive black hole that dates back to the early universe. This black hole is believed to have formed from a star that was similarly low in metallicity. The finding reveals that around 700 million years after the Big Bang, as the universe continued to expand, the supermassive black hole exhibited a reddish hue. This redshift in light indicates a dense surrounding cloud of gas and dust. Lucas Food and Al Zitron from the Buin College of the NG's Space Science team mapped this supermassive black hole by analyzing JWST data. Its impressive mass, approximately 40 million times that of the Sun, starkly contrasts with its host galaxy. The researchers found that the black hole is actively consuming gas and dust in its vicinity, and is located about 12.9 billion light-years from Earth. This process of growth is ongoing. Initially, scientists believed this object resembled a quasar due to its distinctive reddish appearance. Quasars are formed when large amounts of matter surround supermassive black holes, creating a disk of gas and dust known as an accretion disk. This matter is gradually fed into the black hole, and its immense gravitational pull heats the material, producing extreme temperatures and intense light. Furthermore, supermassive black holes and active galactic nuclei (AGNs) emit powerful jets that expel any material not consumed, propelling it at nearly the speed of light, accompanied by bright electromagnetic emissions. The JWST data revealed the black hole as a small point of light due to the vast radiation it emits. This finding suggested it might be an unusual star-forming galaxy based on color analysis, providing additional evidence supporting the existence of supermassive black holes. Its relatively small size and apparent nature set it apart from other quasars identified during that era. Even with the JWST's advanced infrared capabilities, this early quasar would not have been detectable without a phenomenon predicted by Einstein in 1915. According to Einstein's general theory of relativity, massive objects warp the fabric of spacetime, creating gravitational effects. This curvature influences the paths of both planets orbiting stars and light emitted by stars, causing it to bend around massive objects. In cases of extreme gravitational lensing, this effect can distort the appearance of background objects, making them appear in multiple locations within the same field of view. Sometimes the background object is merely distorted due to the enhanced light. This phenomenon, known as gravitational lensing, allowed the JWST to amplify the brightness of distant galaxies that would otherwise remain hidden. In the galaxy cluster known as 2744, the JWST successfully enhanced the visibility of a red quasar that initially appeared as 3 distinct red spots. This new data contributes to the growing body of evidence regarding the formation and characteristics of supermassive black holes in the early universe.